Hello everyone, welcome to the course Nature and Properties of Materials. Today we'll have a summary session. So whatever we have talked in 8 weeks, we'll summarize that today. This course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. I'm your TA, Alka Jangir from IIT Kanpur. So firstly, we started with the introduction to materials, then we throughout the course, then we moved to the mechanical properties, then we talked about metals, polymers, and ceramics, followed by smart materials, composites, then smart materials, and then we talked about design and material selection. Then finally, yesterday we talked about some non-mechanical properties. So today we'll try to summarize all that so that can help you with your final exam. So firstly, material classification. So engineering materials, basically the solid materials mainly that are used. So they are classified into 5 categories. So these are depending on the bonding between them. So in case of metals, you have metallic bonding. So these can be further classified into ferrous and non-ferrous. In case of ferrous, you have iron-based materials, which can be iron and steel and cast iron and other uh, alloys of irons, other alloys of iron. Next, you have non-ferrous metals. So in this, everything except iron that will fall in this category. So copper, aluminum, titanium, gold, silver, tungsten, these will be non-ferrous. So these can be further classified into heavy and light elements. So in case of light, you have aluminum, beryllium, and magnesium, these type of elements and these type of metals and their alloys, zinc, etc. And in case of heavy, you have copper, gold, mercury, and those having higher atomic numbers. Next, you have non-metals. So in this case, you have uh, here you find different types of bonding compared to the metallic bonding or other bonding. So here, in case of non-metals, they can be classified based on their physical state. So they can be gases such as hydrogen, helium, nitrogen, oxygen, and other gases. So these are in molecular forms. Next, you have liquid. So bromine is found in liquid state, and some solids such as carbon, phosphorus, sulfur, selenium, iodine, these are in solid state. Now these metals and non-metals will talk in detail in further slides. Next, you have ceramics. So ceramics can withstand higher temperatures. So these are basically in oxidation state, so such as alumina. So these are oxides or carbides, nitrides, or these can be single element as well, such as diamond, graphite, and coal and other ceramics. So ceramics can withstand higher temperatures, so compared to metals and polymers. Next, you have polymers. These are basically hydrocarbons, and so natural they can be wool and silk, and man-made can be polyethylene, PVC, nylon, bakelite, etc. In case of next, you have composites. So these can be wood, concrete, fiberglass, carbon fiber reinforced polymers, glass fiber reinforced polymers. So in this case, carbon fiber will be your reinforcement and matrix will be of plastic or polymers. Okay, so next up, For metals, so metals are characterized by the following properties. So firstly, you have physical properties. So they are good electrical and heat conductors because of the presence of free electrons. So the in case of metallic bonding, your ion there'll be formation of ion cores, and surrounding that will be electron cloud. So this electron cloud is loosely bound to the ion cores. So these electrons are free to move. So they are good conductors of electrical and thermal heat. Next you have malleability. So in case of if you compress it with hammer or other equipments, then they can be formed into thin sheets. And next you have ductile. So ductility is you can draw it in thin wires. So these can be stretched into thin wires. So these have high ductility and they possess metallic luster. And also they are solid at room temperature except mercury. Next you have chemical properties. So they usually have 1 to 3 electrons in the outer shell, and they lose their valence electrons very easily because they are loosely bound. And these form oxides that are basic, such as sodium oxide or potassium oxide, magnesium oxide, aluminum oxide. These all act as basic, and these are good reducing agents. So they lose electrons easily, that's why they are reducing agents. And they have lower electronegativity and tendency to uh, electronegativity can be defined as tendency to attract electrons. So they have lower electronegativity, so they don't attract electrons. And next you have these are the some metals. So cast iron, wrought iron, aluminum, steel, these all are used widely in engineering applications. Next you have non-metals. So non-metals are characterized by the following properties. So in case of physical properties, they are opposite of metals. So they are poor conductor of heat and electricity. Some non-metals are good conductor of heat as well, but widely they are poor conductors of heat and electricity. They are brittle if in a solid state, and they are non-ductile and do not possess any metallic luster. They are transparent when they are in thin sheet form, and they can be solid, liquid and gas at room temperature. In case of chemical properties, so they have 4 to 8 electrons in the outer shell. So they have tendency to gain or share valence electrons easily, and they form oxides that are acidic. So for example, nitrogen oxide, sulfur oxide, these all are acidic in nature. So they when they combine with H2O, then they form some acids such as nitric acid, sulfuric acids and so on, HCl and others. And these are good oxidizing agents, and they have very higher electronegativity. So diamond and coal, charcoal, these are the some of the examples of non-metals. Then you have ceramics. So in case of ceramics, they are materials which are inorganic materials made from compounds of metal and non-metal. So for example, aluminum and oxygen, they combine, they'll be forming alumina. And in these are formed by the action of heat and subsequent cooling, and they are brittle in nature, and they are good insulator of heat and electricity. So and they are also excellent in compressive strength. So when they are stressed using tensile strength, then they are very weak, but when you are compressing, then even though they have presence of pores and some defects like pores and cracks, micro cracks, so in case of compression, they don't they don't break easily. Now, some of the applications of ceramics are in making roof tiles, bearings. So in case of bearings, you can use silicon nitride and other um, boron carbide and other ceramics. Ceramic coated turbine blades and pottery, these all are made using ceramics. Next you have polymers. So a polymer is a large molecule composed of many repeated subunits, and these can be of two types. So natural polymers, which will be having such as amber, wool, silk, natural rubber, etc. And synthetic polymers, in this case you'll be having synthetic rubber, bakelite, neoprene, nylon, polystyrene, polyethylene and PVC, etc. These are some of the applications of polymers in making these bottles, tires and all these snooker balls, plastic spoons, etc. Next you have composites. So this is the combination of previous categories. So if you combine let's say polymer and metal, or you combine polymer or ceramic, these will give you formation of composites. So two or more constituent materials with significantly different properties, which after combination produces a material with characteristics different from the individual components, and the individual components remain separate and distinct within the finished structure. So for example, fiber, when it is combined in the matrix, embedded in this matrix, it will form a fiber reinforced composite. Now for the mechanical properties, so first and foremost is stress and strain. So these are the parameters. So stress can be defined as the internal resistance, force per unit area acting on a material. So in this case you have it uses the original cross section area of the specimen and is also known as engineering stress or conventional stress. So sigma is equals to F upon A naught. So F is your force that you are applying and A naught will be your cross section area, initial cross section area. Unit will be, so force has unit of newtons, area is meter square, so Newton per meter square, or you can easily say Pascal or megapascal, these are the units. Now in this cylindrical root, you can see if you are applying force, your this original shape will change into final length L. L naught will change into small l. So, and if you are applying compressive type of force, then also it will change its initial to last L. Now strain is defined as the change in length per original length, and it is unitless and also known as engineering strain or conventional strain. So strain will be delta L upon L naught. L naught is original length, and sometimes strain is expressed in microstrain. So 1 micron strain will be 10 to the power minus 6. Next we have, to connect this stress and strain, we have Hooke's law. So in this case, within the elastic limit, so for low strain values, the stress is directly proportional to strain. So the behavior of solid is linear elastic, and the constant of proportion is called elastic modulus. So sigma equals to capital E times epsilon. It also holds good for stresses and strain in simple compression. So in the same way, shear stress tau is proportional to shear strain gamma. So tau is equals to G times gamma, where G is your shear modulus. And also in case of the pressure is proportional to the negative of the dilation volumetric strain, because positive pressure causes a shrinkage of volume. Hence, P equals to minus K times delta V upon V. Here K is bulk modulus. And all these elastic shear and bulk modulus, they have same dimension as that of stress as pascals. So when you are trying to stretch your material, so regarding that, it will have some stress induced in your material, so that stress is plotted on y-axis. So as you keep on increasing your strain in material, your stress will keep on increasing depending on properties of material. So initially it will show linear behavior, after that it will show yielding in material, and then it will show strain hardening. So up to this point, just the bond stretching between the atoms is taking place, and after this point it is showing some dislocation movement. So dislocations will keep on moving and interacting with each other, leading to strain hardening. So a material will get harder, and after this point this corresponds to the necking. So in this area your cross section area decreases very fast. So at a particular point you will see some formation of neck. So in this, so your stress drops very fast because the area corresponding to that neck is very lower compared to original area. Okay, so next you have elastic limit. So the greatest stress that a material can withstand without any measurable permanent strain after unloading. And yield strength is stress at which a material begins to deform plastically. Now determined by the stress corresponding to the intersection of the stress strain curve and a line parallel to the elastic line, offset by a strain of 0.2%. And the tensile strength or ultimate tensile strength is maximum load P max divided by the original cross sectional area A naught of the specimen. So this will be corresponding to the maximum point in case of engineering stress strain curve. In case of elongation, this is simply final length minus initial length divided by initial length times 100. And in case of reduction in area, so area will keep on reducing, so you have to take initial area minus final area divided by initial area times 100. Next you have true stress and strain. So in case of true stress strain curve, it gives a true indication of deformation characteristics because it is based on the instantaneous dimension of the specimen. In engineering stress strain curve, stress drops down after necking since it is based on the original area. And in true stress strain curve, the stress however increases after necking since the cross-sectional area of the specimen decreases rapidly after necking. And the flow curve of many metals in the region of uniform plastic deformation can be expressed by the simple power law. So this power law is sigma T equals to K times epsilon T to the power N. Here your sigma T is your true stress and ET is epsilon T is true strain, K will be your strength coefficient, N is strain hardening exponent. So this strain hardening exponent will be 0 in case of perfectly plastic solid, and N will be 1 for elastic solid, and for most metals it will be between 0.1 to 0.5. So in case of when you plot this true stress strain curve with the engineering plot, it will always be above this engineering plot because you are dividing it with the smaller area. So the true stress will be higher compared to this, and the points will be shifted to the left side. Next you have ductility and brittleness. So depending on the fracture in material, your material can be either ductile or brittle. In case of ductility, it measures the degree of plastic deformation that has been sustained at fracture, and strain at fracture is greater than 0.05, or percent elongation is greater than 5%, and these materials have well defined yield point. In case of brittleness, the material that experiences very little or no plastic deformation upon fracture, so your strain will be less than 5%, and they don't exhibit any identifiable yield point. So you can see in this B curve that there is no identifiable yield point. So this material shows a ductile behavior. So here percent elongation is very higher compared to this material. So this is the characteristic of some ceramics and non-metals, and this is for ductile is characteristic of mainly metals and polymers. So this is a material. So this shows a brittle type of failure, and here this shows a ductile type of failure. So in this case you'll see necking, then after that you'll see some void nucleation. So voids will start to form, pores will collapse, and void coalescence will occur, which will lead to formation of a crack. So this crack will propagate through the entire cross section, and it is at an angle. It is around 45-degree angle or so, and then you'll see separation of the specimen. Resilience. So resilience is the capacity of a material to absorb energy when it is deformed elastically and then recover same upon unloading. So modulus of resilience, which is the strain energy per unit volume required to stress a material from an unloaded state up to the point of yielding. So SI unit is joule per meter cube. So here, so from this curve you can see up to yield point, you take this entire curve and you integrate this curve. So there can be, you can either divide this curve into small rectangles and measure the entire area, or you can either, in case of when you have all the curve, the data is available for various data points at the curve, then you can use that method. Otherwise this can be approximated in terms of yield, your yield stress and your yield strain. So this, as you can see, it is a similar to a triangle, right? So for this triangle you can say this is your EY times the sigma y, then you put half for the triangle. So this will be half times sigma y times epsilon y. Now from the Hooke's law you can write this strain in terms of elastic modulus, which you will be knowing, and this becomes sigma y square divided by 2e. Now for resilient materials, they have high yield strength and low modulus of elasticity. For example, beryllium copper, and this beryllium copper, it is used in spring applications. Next you have toughness. So toughness is also energy as resilience, and this is the area under the entire curve. So it is measure of ability of material to absorb energy up to fracture. It is represented by the total area under the stress strain curve up to the fracture point, right? So brittle material, they have comparatively high yield and tensile strength, but low toughness due to the lack of ductility. So here for a brittle material you can see it has high yield strength as well as tensile strength, but the area under the curve is very low because the ductility is lower. And ductile materials are tougher than the brittle ones. Next you have impact testing. So in these tests, load swings from a given height to strike the specimen, and the energy dissipated in the fracture is measured. And the metallic samples, they tend to be square in cross section, while polymeric test specimens are often rectangular. And the factors that affect impact energy are, for a given material, the impact energy will be seen to decrease if the yield strength is increased. And the notch serves as a stress concentration zone, and some materials are more sensitive towards notch than the others. And most of the impact energy absorbed by the means of plastic deformation during the yielding, and therefore factors that affect the yield behavior and hence ductility of the material, such as temperature and strain rate, will affect the impact energy. And now from this graph you can see that the ceramics have the lowest impact strength, and above that they have polymers and composites, and metals have the intermediate and highest. Some of the metals have highest impact strength, such as pure ductile metals and beryllium and all. These have lower side of impact strength. Next you have hardness. So it is the surface property. So it is a measure of a material's resistance to localized plastic deformation. For example, it can be a small indentation or a scratch. The advantages of hardness testing: it is simple and inexpensive, and no test specimen preparation is needed, and the apparatus is relatively cheaper. And the non-destructive method, and it has small indentation, is the only deformation. Other mechanical properties like tensile strength and fatigue strength, they can be obtained from the hardness data. So there is some empirical relationships for particular materials. For example, for steel and for brass and other metals, there are approximated relationships between tensile strength, fatigue strength and hardness. Now one of the older method to measure hardness is Mohs scale. So it is based on the ability of one material to scratch another, and hardness is measured on a scale from 1 to 10, 1 being the softest, 10 being the hardest. Now these are the hardnesses given for various minerals. So for talc it is kept 1, and for diamond it is kept 10, and in between those you have such as calcite having hardness as 3. So this diamond, it has the highest hardness among these minerals. Next up you have macro hardness test. So in these you have Rockwell, Brinell and Vickers hardness test. In micro you have Knoop hardness and Vickers micro hardness test. Now these are the various indenters and loads that I used. So in case of Brinell, you use 10 mm steel or tungsten carbide balls. So these are spherical balls having load between 500, 1500 or 3000 kg. And this is the formula that is used, which depends on load and the diameter of indenter and indentation. For Vickers, you have diamond pyramid having 136-degree angle, and the diagonals are measured, and these diagonals length is given as L, and this formula is used. So load can be from 1 to 120 kg. It can also be in gram force in case of micro indentation. In case of NUP, you have diamond pyramid, so you have diagonals at different length. So in this case you measure the longer diagonal and use this for measurement of hardness. In case of Rockwell hardness, you have various scales, and based on those you have three types of indenters. So you can have diamond cone, which is all with diamond cone having 120-degree angle, and you can have 1/16-inch diameter steel wall, or you can have 1/8-inch diameter steel wall. Now this diamond cone, this indenter is also called Braille indenter. Now A, C, D, these scales fall in this, and the loads that are used are given here, and the formula used is 100 minus 500 times T. T is your depth of penetration. Next up you have creep. So creep strain, in this case you have permanent deformation under constant load over a period of time. So dependent on the temperature, and temperature is also kept constant, and you study with time how your strain changes in material. So with increasing temperature your creep will occur faster. And a creep test, it involves a tensile specimen under a constant load maintained at a constant temperature. At relatively high temperatures, creep appears to occur at all stress levels, but the creep rate increases with increasing stress at a given temperature. The applications are in studying the material behavior at elevated temperatures, such as turbine blades, nuclear reactor components, jet engines, heat exchangers, etc. And creep occurs in three stages. Primary stage, so up to this part, this is a primary stage which occurs at the beginning of the tests, and creep is mostly transient. Then this is the steady state, also known as secondary state. In this case your creep rate is roughly steady. Next is tertiary stage. In this your creep rate begins to accelerate as the cross-sectional area decreases due to necking, followed by failure known as rupture. Now next is periodic table. So in this we know that when you go along the columns you see valence structure remains same. So all these have, for example, first group has one unpaired electron in their outer shells, and in this beryllium, magnesium, calcium you have two electrons which are paired. Now because of the similar electron structure, valence structure, they have similar properties, and as you keep going in this direction, right direction, you see that electronegativity increases and it readily acquires electrons to become negative ions. So fluorine is the most electronegative element, and when you move in this left hand side, you see electropositivity increases. So your elements, they readily give up electrons to become positive ions. In this case you have cesium as the most electropositive element. Now atomic bonding can be of two types. First is primary bonding. These are relatively strong, and these materials melt between 1000 to 4000 kelvins. So the types of primary bonding is covalent, ionic and metallic bonding. Next you have secondary bonding, which is relatively weak, and these materials melt between 100 to 500 Kelvin. And examples are van der Waals bonding and hydrogen bonding. Next you have ionic bonding. So it is found in compounds that are composed of both metallic and non-metallic elements. So large difference in electronegativity is required, which means bonding occurs between elements situated at the periodic table's horizontal extremities. It requires electron transfer to achieve stabilized outermost electron configuration, and the bonding forces are coulombic, and the attraction between the opposite charges. So NaCl, AgCl, these are on extremes of the periodic table. So from this side and this side, when you will be seeing bonding, it is more likely to be ionic bonding. Alumina, magnesia, lithium fluoride, these all are ionically bonded. In case of ionic bonds, they are non-directional because the magnitude of the bond is equal in all directions around an ion, and higher melting point because of large bond energy, typically 600 to 1500 kilojoule per mole, or 3 to 8 electron volt per atom, and they are often hard and brittle materials. Now, ionic solids are good insulators of electricity in their solid state and good conductors of electricity in their molten state. Next is covalent bond. So in this case, stable electron configurations are obtained by the sharing of electrons between adjacent atoms, and the covalent bond is directional in nature, means it occurs between specific atoms and only in direction between one atom and another that participates in the electron sharing. The number of covalent bond for a particular atom is given as 8 minus n. Here n is the number of valence electrons that are present. Now example is non-metallic molecules such as hydrogen, H2, F2, Cl2, etc. and molecules containing dissimilar atoms but sitting not that far apart in the periodic table, such as CH4. So electronegativity is not that much different for carbon and hydrogen and oxygen, H2O, HNO3, HF, etc. Elemental solids such as diamond, silicon, germanium. Solid compounds, gallium arsenide, indium antimonite, and silicon carbide. Polymers, they also contain secondary bonds. So along the chain, they have covalent bonding, and between two chains, you'll be finding out secondary bonding. Next, we have metallic bonding. So it is found in metals and their alloys. So metallic materials have at most 3 valence electrons which are not bound to any particular atom in the solid, forming an electron cloud. Okay, so these are the ion cores, and the sea of valence electrons, this is electron cloud, and the rest of the non-valence and atomic nuclei, they form ion cores having a net positive charge, and there is a force of attraction between valence electrons and metal ions. Free electrons act as a glue to hold the ion cores together, and the metallic bond imparts properties such as strength, malleability, ductility, luster, conduction of heat, and electricity. Next, you have hydrogen bonding. It is strong dipole-dipole attractions that involve molecules with OH, NH, and FH groups. So example is water. So in case of water, it expands upon freezing. So when you freeze a water, so there will be formation of hydrogen bonds. So this will lead to some space between two molecules, leading to expansion. So in solid ice, each water molecule participates in 4 hydrogen bonds, and the hydrogen bond keeps molecules apart. This relatively open structure That's why ice has a lower density than liquid water and it floats. Van der Waals bonding in this weak is it is weak in comparison to primary bonding, and bond energy is of order of 0 0.1 electron volt per atom, and it occurs to some extent in all materials but is particularly important in plastics and polymers. It results from attraction forces between electric dipoles. Now bonding in materials, so you have ceramics, metals and polymers. In case of ceramics, we'll be having ionic and covalent bonding. So these have high bond energy leading to high melting temperature, large elastic modulus and small thermal expansion coefficient. In case of metals, you have metallic bonding which has variable bond energy, moderate melting temperature, moderate elastic modulus and moderate thermal expansion coefficient. In case of polymers, you have covalent and secondary bonding. So along between two chains you have secondary type of bonding, and along the chain between carbon and other atoms you see covalent type of bonding. And this covalent bonding gives it directional properties. Secondary bonding is dominating, so it has small melting point and elastic modulus but large thermal expansion coefficient. Now types of solids. So first you have crystalline solid. So in this case a long range structure exists in which atoms are arranged into unit cells and the unit cells repeat in a regular order pattern, and these form a 3D lattice, and these have directional properties, so having an isotropic nature, and these have sharp melting points. Examples are gold, silver, aluminum and other metals. Polycrystalline solids, so these are made up of an aggregate of many small single crystals, also called crystallites or grains, and across grain boundaries the orientation of crystal changes. So as here okay, so now these are the grain boundaries, and in this side and this side you can see that the orientation is changing, and the grains are usually 100 nanometer to 100 microns in diameter, and polycrystalline materials have a high degree of order over many atomic or molecular dimensions. Polycrystals with grains that are less than 10 nanometer in diameter are called nanocrystalline, and most engineering materials are polycrystalline. Properties may or may not vary with direction, and example is common steel is polycrystalline, and if grains are textured due to rolling then anisotropic, and if grains are random then it shows isotropic properties. Next you have single crystal. So it has only one grain and no grain boundaries. It is formed by uniform cooling of liquid material. So it can have some other defects such as vacancies and other dislocations, but it won't be having grain boundaries. It has high degree of order throughout the entire volume of the material, and it is useful for applications where grain boundaries are harmful, such as high temperature deformation or creep resistance, as creep takes place by grain boundary sliding. And single crystal turbine blades, nickel based superalloy gas turbine blades, which can withstand creep at high temperature due to lack of grain boundaries. So grain boundaries, at higher temperatures they provide higher diffusion, so that can be detrimental to the material at higher temperatures. And also in case of diamond, it is single crystal, and for semiconductors when you trying to dope any semiconductor, so then you want this doping to be uniform throughout, otherwise there will be variation in conductivity along the area of your material. So to prevent that, you want to have a material with no grain boundaries. So single crystalline silicon is uh, single crystalline silicon is preferred to having a polycrystalline silicon. Next you have amorphous solid. So the atoms or molecules are arranged in a irregular manner and there won't be any periodic packing, and these have no directional properties and they have isotropic properties. These occur for complex structures and also rapid cooling. So for example, glass, plastic, rubber, etc. So for example, if you have a material with more than 4 or 5 elements, so you are basically confusing the system to which unit cell to obtain. So if you are cooling this system after melting for having 4 or 5 elements, then it is uh, more likely to solidify in an amorphous structure. And if you rapidly cool, even having 1 or 2 elements, then if you are rapidly cooling it, then it will solidify in amorphous structure, because it won't be having that time to go and sit at the unit cell points, right? So here for example silica structure is given, which is amorphous in nature. Next you have unit cell. So unit cell is the smallest block or geometrical figure from which the crystal is built up by repetition in 3 dimensions, and the fundamental grouping of particles which are repeating entities. Unit cell is the basic structural unit or building block of the crystal structure, and a crystalline solid can be constructed from a unit cell plus translation vector. So you have this unit cell, and if you're translating it along the x-axis, then you find this. This is 1D lattice, and if you translate in y-axis, then you have 2D, and if you translate it along z axis as well, then it is a 3D unit. Okay, now next, in case of crystal systems, you have first lattice. So lattice is a mathematical representation. So it is array of points in space in which every point has an identical environment with respect to all other points, and the basis is single atom or group of atoms which are identical in composition and orientation in space. Now both of these combined, if you put bases at the lattice points, then you will be having a crystal structure. And these are the various crystal systems, 7 crystal systems that are possible: cubic, hexagonal, tetragonal, rhombohedral, orthorhombic, and monoclinic, triclinic. So this is as you are going down. So cubic has the highest symmetry and triclinic has the lowest symmetry. Next you have Miller indices. So in Miller indices, these are the designation of the planes and direction in the unit cell, and the number of indices will match with the dimension of the lattice or the crystal. For example, if you have 3D, so the unit cell has 3 indices, namely HKL. If you have commas in between, then it will represent a point. If there is no comma, then it will be a Miller indices. So these are various symbols that I used. So this smaller bracket is used for individual plane, curly bracket is used for family of planes, square bracket is used for individual direction, triangular bracket is used for family of directions. Now Miller indices of planes. So in case of planes, you basically uh, first you choose an origin, right? So O in the unit cell such that planes does not touch the origin and plane is closest to the origin. Then you mark intercepts from the chosen origin along x-axis, along y-axis, along z-axis. So you take the reciprocal of the intercepts 1 upon a, 1 upon b, 1 upon c, and you modify the reciprocals. So you make them whole numbers. So you reduce the multiples, you eliminate fraction, and you put bar above the negative integer in indices if there is any. And then you place round bracket around the indices. So this is one type of plane. In case of Miller indices of a direction, you have to basically choose an origin and walk along the direction. So first you have to create origin, O dash at tel if necessary, and label O dash and the new axis as x, y, z dash. So you have to find coordinates from the tel at O dash to the head of the direction. Then you have to eliminate, reduce multiples, eliminate fractions and use bar for negative and place square brackets. Next is crystal defects. So any deviation from the crystal's completely ordered arrangement of constituent particles is called a defect or imperfections. And the properties of material are influenced by the presence of imperfections. The mechanical properties of pure metal, they change significantly when metals are alloyed. And the classification is 0D, 1D, 2D and 3D. So in case of 0D, you have vacancy defect, interstitial, substitutional, Frankel and Schottky defect. In 1D, you have edge, screw and mixed type of dislocations. In 2D, you have 2D or planar defects, you have grain boundaries, twin boundaries, free surface, etc. In 3D, you have voids, cracks, etc. In case of vacancy defect, so when an atom is missing from regular lattice site, it is called vacancy. So it is impossible to create a material free from vacancy defect, and the presence of vacancy increases entropy or disorder in the crystal. So it decreases the density of the substance. The concentration of vacancies increases with increasing temperature and decreasing activation energy, which is the energy required for the formation of vacancies. So this activation energy depends on metals and type of bonding. Now equilibrium vacancy concentration can be given as exponential minus QV upon KBT. KB is your Boltzmann constant. Next is grain boundaries. So boundaries separating the two grains or crystals having different crystallographic orientations in polycrystalline materials, and the atom near the boundaries are slightly disordered and have higher energy than those within the grains. And in general, a grain boundary has 5 degrees of freedom, and we need 3 degrees of freedom to specify the orientation of one grain with respect to other. Now from this this image you can see you can have small angle grain boundaries and high angle grain boundaries. So firstly you define whether you want to choose 5 degree or 10 degree. So above 10 degree you will be defining as high angle grain boundaries, and below that you will be defining small angle grain boundaries. So your orientation will change according to that. Now from the metals topic, so firstly metals can be classified into ferrous and non-ferrous. So I told this earlier as well. And in case of ferrous, if you have carbon less than 2.1 weight%, this will be steel. If higher than that, then it will be having cast iron. So steel can be classified further as low alloy steel and high alloy steel. In case of low alloy steel, you have low carbon steel, less than 0.25 weight% carbon. In medium carbon steel, you have 0.25 to 0.6 weight% carbon. In high carbon steel, you have 0.6 to 1.4 weight% carbon. In high alloy steel, you have tool steel and stainless steel. So first you have low carbon steel. So these contain carbon less than 0.25 weight%, also known as mild steel. And these are relatively soft and weak, and they have outstanding ductility, around 25% elongation and toughness. They also have high machinability and weldability, and they are least expensive to produce. And the tensile strength is 415 to 550 MPa. The applications are in beams, channels, nuts, bolts, wires, tin cans, etc. In case of low alloy steel, it contains alloys such as copper, vanadium, nickel, and molybdenum up to 10 weight%, high strength and corrosion resistance than plain carbon steel. Next, their tensile strength is also up to 700 MPa. In case of medium carbon steel, you have 0.25 to 0.6 weight% carbon. These are stronger than the low carbon steels, but they have low ductility and toughness. They have good wear resistance, and plain carbon steel has tensile strength up to 850 MPa, and alloy steel has around 1900 MPa. Applications are in railway wheels, tracks, gears, crankshaft, and etc. In case of high carbon steel, we have more than 0.6% carbon. These are hardest, strongest, and least ductile carbon steel. These can be alloyed with carbon and other metals to form very hard and wear resistant materials such as chromium, nickel, tungsten, molybdenum, and vanadium. Applications are in cutting tools, dies, saws, concrete drills, etc. Tool steels. Now these are commonly used in drill bits and other rotating cutting tools. It can withstand higher temperature without losing its hardness and toughness. And the examples are 1841 HSS. This is 18% tungsten, 4% chromium, and 1% vanadium with a carbon content of 0.6 to 0.7%. Cobalt high-speed steel, it shows increased heat resistance. Molybdenum high-speed steel, it has molybdenum increases hardness and wear resistance. Also a cost-effective replacement for tungsten in tool steels. Now stainless steel, it is highly resistant to corrosion in a variety of environments, and predominant alloy element is chromium, which is at least 11 weight%. Example is 18H stainless steel, in which you have 18% chromium and 8% nickel. And depending on the combination of chromium and nickel, you can have various types of stainless steel such as austenitic, ferritic, and duplex type of stainless steels. Applications are in cryogenic vessels, food processing equipments, gas turbine parts, high temperature steam boilers, heat treating furnaces, nuclear power generating units, etc. Next is cast irons. Now there are mainly 4 types of cast irons. So gray, white cast iron, malleable, and ductile cast iron. So first you have gray cast iron. This is the basic microstructure. So in this you have this graphite flecks, which you can see, right? So these graphite flecks are surrounded by ferrite matrix. So the graphite carbon content varies from 2.5 to 4 weight%. Graphite exists in the form of flecks, and these flecks, they give self-lubricating properties and vibration damping capacity. and the strength and ductility are much higher under compressive loads. Tensile strength is between 120 to 280 MPa. Applications are base structures for machines and heavy equipment that are to exposed to vibration. Next you have white or chilled cast iron. So in this you don't have any graphite and carbon is in form of carbide, cementite, which is hardest constituent of iron. It is formed by rapidly cooling molten iron and very hard, wear and corrosion resistant. These are almost non-machinable and applications are in rollers and rolling mills. This is the microstructure. Next you have malleable cast iron, which is formed by heating white cast iron. So heat treatment is between 800 to 900 degrees Celsius for prolonged time in a neutral atmosphere to prevent any oxidation, which leads to the decomposition of the cementite, forming graphite in the form of clusters. And it is highly shock resistant or tough, and the tensile strength is between 350 to 450 MPa, and it can be hammered to a small thickness, and applications is in case of connecting rods, transmission gears, pipe fittings and ball parts. In case of next is ductile, nodular or spheroidal cast iron. It is obtained by adding some small amount of magnesium or cerium or these type of elements around 0.1 to 0.8% to molten grey cast iron, and this leads to formation of graphite in the form of spheres. It shows high fluidity, toughness and wear resistance, and it has high strength around 400 to 900 MPa. It shows good machinability and buildability. Now strengthening mechanisms in metals. So the ability of metal to plastically deform depends on the ability of dislocation to move, thus restricting or hindering dislocation motion, which makes a material harder and stronger. Some mechanisms of strengthening metals are grain refining, solid solution strengthening, strain hardening, precipitation strengthening, martensitic strengthening and composite strengthening. In case of grain refining, so here you have a fine grained material, one that has small grains, and it is harder and stronger than a coarse grain due to a greater total grain boundary area to restrict dislocation motion. So here sigma naught is equals to sigma I plus ky upon root d. So here sigma naught is the yield strength of material, sigma I is frictional stress opposing motion of dislocation, and ky is the extent to which dislocations are piled up, d is average grain size. So here sigma I depends on the type of crystal structure, so FCC, BCC and other factors. Ky depends on the amount of rolling or other plastic deformation that you have provided to the material. D is your average grain size. So your grain refinement, so as the grain size of the material decreases, your strength of material will increase, and the critical grain size, which is typically around 10 nanometer, the yield strength would either remain constant or decrease with decreasing grain size, and this phenomena is known as inverse Hall-Petch relation. So this one is your Hall-Petch relation. In this case you can see the motion of a dislocation. So this dislocation is moving and will face a barrier at the grain boundaries because there is change in orientation along this grain boundary. So will be more stress will be required for this dislocation to move in the material. Next, you have solid solution strengthening. In this case, you have pure metals which are almost always softer than their alloys. And adding another element that goes into interstitial or substitutional positions in a solution increases strength. And the impurity atoms, they cause lattice strain which can anchor dislocation. Those alloys are stronger than the pure metals. So for copper nickel, you can see as you keep on increasing amount of nickel, you see tensile strength increases and the ductility reduces. Strain hardening, it is the enhancement of strength with increased plastic deformation. And the strain hardening is the phenomena whereby a ductile metal becomes harder and stronger as it is plastically deformed. And it is also called work hardening or cold working because the temperature at which deformation takes place is lower than the melting temperature. And the effects of strain hardening may be removed by annealing heat treatment and such as slow heating and slow cooling, and strength increases but ductility is sacrificed. So here you can see as the dislocation amount increases, the required stress also increases. So dislocation density with stress on the material, and this amount of stress also, as you keep on deforming your material, there will be more formation of more dislocation forest. Precipitation or edge hardening. Now this is mainly seen in aluminum, copper type of system alloys, and also in some steels also you see this precipitation hardening. So this is a technique that is used to increase the yield strength of malleable materials like aluminum, copper alloys, stainless steels, etc. Now based on changes in solid solubility with temperature to produce fine particles of an impurity phase which blocks the movement of dislocations in a crystal's lattice. Now alloys must be kept at elevated temperature for hours to allow precipitation to take place, and this time delay is called aging. Now in this case you can see in aluminum matrix you have copper atoms which are more likely at the time of aging they'll come together and form some precipitates. Now there are various phases such as theta double prime, theta, and then finally GP zones on such precipitates. So this is the aging cycle. So first you provide some solution heat treatment. So after that you quench your material. Now this copper will be distributed in the matrix and you heat your material again at the lower temperature compared to this solution heat treatment temperature. Then you find that there will be formation of some precipitates with the increasing time. Corrosion of metals. So for good oxidation resistance, the oxide should be adherent to the surface, and this is the pilling Bedworth ratio, which is volume of the oxide formed divided by volume of metal consumed in the oxidation. Now if this ratio is lesser than 1, then there will be tensile stresses in oxide film which make this, so here as it is shown, brittle oxide will crack and will become unprotective. If this is between 1 and 2, then there will be compressive stresses in oxide film and uniformly over a metal surface and it will become protective. If this is greater than 2, then there will be high compressive stresses in oxide film. This oxide will crack and flake off and become unprotective. Now between alumina and chromia, these are the ones having protected oxide layer. So alumina, nickel oxide, copper oxide, these are nicely protected, but as we know, in iron this oxide layer is not that much protective, and it leads to further corrosion of material. And in potassium, sodium, magnesium as well, there is presence of tensile stresses. Now next is ceramics. So ceramics is derived from the word, which means a Greek word which means burnt stuff. So it is oxides, that's why it is called ceramics. So clay is the earliest known ceramic used for making potteries. So ceramic materials, they are inorganic crystalline materials made from compounds of a metal and a non-metal, primarily held by ionic and covalent bonds. And the glass by definition is now a ceramic because it is an amorphous solid, but its mechanical properties behave similarly to ceramic materials. Some of the common characteristics are hard and brittle, strong in comparison, typically 10 times, weak in tension, chemically inert, insulators of heat and electricity, except carbon in form of diamond and graphite. So graphite is electrical conductor, diamond is an thermal conductor, high and well defined melting points. Bonding in ceramics, so these can be ionic and covalent. So many ceramics exhibit a combination of ionic and covalent bonding types, and the degree of ionic character being dependent on the electronegativity of atoms. And ionic ceramics, they have ionic bonding is predominant. They are compounds of metal with non-metal, and the electrostatic attraction between the unlike charges is responsible for dense packing. Examples are NaCl, MgO, zirconia, alumina, etc. Covalent ceramics they have covalent bonding as predominant, and they are compounds of two non-metals or occasionally pure elements such as diamond and carbon. Bonds are formed by sharing electrons with their neighbors to give a fixed number of directional bonds. Examples are silica, graphite, diamond, etc. Now these are the various classifications for polymers. Now based on the molecular structure, so they can be linear and branched. In case of linear, your units are joined together end to end in single chains, and there may be some weak van der Waals and hydrogen bonding between two different chains. And these are soluble and fusible. Examples are high density polyethylene, PVC, polystyrene, nylon, PMMA, etc. In case of branched, you have side branch chains which are connected to the main ones. These are more soluble and fusible, and examples are low density polyethylene. So because of these branches, there will be more open structure leading to lower density. Cross-linked. Now adjacent linear chains are joined one to another at various positions by covalent bonds. These are insoluble and infusible. Network, so you have high cross-linking and 3D network. These are insoluble and infusible. Examples are rubber and polyurethanes and phenol formaldehyde. Classification based on thermophysical properties. Now thermoplastics and thermosets are the classifications. In case of thermoplastic, they are heat sensitive, so they soften and flow upon heating, and they remain soluble and fusible under many cycles of heating and cooling, and they are recyclable. The most linear polymers and those having some branch structures with flexible chains are thermoplastics, and the individual polymer molecules are held together by weak secondary forces, van der Waals forces, hydrogen bonds, dipole-dipole interaction, easy to repair by welding, solvent bonding, etc. And they have unlimited shelf life. So they won't undergo any polymerization during storage or in processing unit. One of the disadvantages is that they are prone to creep. In case of thermosetting, they are network polymers and they are creep resistance. They have less sensitivity to temperature, and they attain permanent hardness due to cross-linking, and they do not soften and flow upon heating. They they are not post formable and obtained in a soluble or fusible stage in the early or intermediate stage, but once they get cured, they will be infusible and insoluble. They are excellent thermal and chemically stable once polymerized, and disadvantage is that they are brittle and non-recyclable. Next is composites. So in this case you have particle reinforcement, fiber reinforcement, or some structural composites. Particle reinforcement can have large particle or dispersion strengthened. Structural can have laminates and sandwich type of structures. Now large particle composites, examples are concrete, which is composed of cement and sand and gravel. The particulate phase is harder and stiffer than the matrix. Reinforcing particles, they tend to restrain the movement of the matrix phase in the vicinity of each particle. The matrix transfers a fraction of the applied load to the particles. Improvement of mechanical behavior depends on strong bonding at the matrix particle interface. So cement plus sand, stone and waters will be concrete. Next you have dispersion strengthened composites. So in this case your particle size will be smaller, between 10 to 100 nanometer, and your strengthening occurs on the atomic or molecular level. Matrix bears the major portion of the applied load, while the small dispersion particles, they hinder the motion of the dislocations. Thus plastic deformation is restricted such that yield and tensile strengths as well as hardness improves. Now these dislocations, they find barrier in form of these dispersion that are present. So these dispersions can be in form of ceramics or other particles. So these can be alumina, silicon carbide, etc. Fiber reinforced composites. So on the basis of diameter and character, so based on diameter and character, fiber phase can be grouped into whiskers, fibers and wires. In case of whiskers, they are very thin single crystals that have an extremely large L by D ratio, but have to have the form of fiber. These are flow free and thus extremely high strength, but they are expensive. Include graphite, silicon carbide, nitride, aluminum oxide, etc. Fibers, they have this L by D ratio equal to 10:1, and either polycrystalline or amorphous, and generally polymer and ceramics. Wires are relatively large diameters, and typical materials include steel, molybdenum and tungsten. Now fiber reinforced composites, so you have two phases, you have matrix and fibers. So your matrix will bind fibers together, your matrix will enhance stiffness, enhance strength and provide crack bridging to enhance thermal resistance. And in case of this matrix, it binds this together, protects the individual fiber from the damage by the external environment, acts as a medium to transmit and distribute externally applied stress to the fiber, serves as a barrier to crack propagation. The requirements of composites is the matrix material should be ductile, elastic modulus of fiber should be much higher than the matrix, and there should be adequate bonding between the matrix and fibers. Next is metal matrix composite. So in this case your matrix will be ductile metals such as aluminum, magnesium, titanium, copper, fiber will be carbon, silicon carbide, boron, aluminum oxide, etc. Advantage of these is that they can be operated at high temperatures, they are non-flammable, and greater resistance to degradation by organic fluids. And also demerits is MMCs are costlier than PMCs. In case of polymer matrix composites, you have glass fiber polymer. So in this case, you have matrix as plastic, which is most often epoxy, polyester resin, etc. Reinforcement can be glass fiber, and they are easily drawn into high strength fibers from molten state, and limitation is service temperature is up to 200 degrees Celsius because your polymer will start to deteriorate. Next you have ceramic matrix composites. So in this case you have ceramics that are highly brittle in nature, thus they have low fracture toughness, and in general the fracture toughness of these ceramics is 1 to 5 MPa root meter, and in case of metal alloys you have 20 to 90. So by using CMC, fracture toughness can be increased to lie in the range of 6 to 20 MPa. Now your crack initiation normally occurs within matrix phase, whereas crack propagation is hindered by particles, fibers or whiskers. And these exhibit improved high temperature creep behavior and resistance to thermal shock. Now brake disc skin of Ferrari race car, this is made by carbon fiber reinforced in silicon carbide matrix. This is one of the application. Now okay, that's it from my side. you have any query, you can ask.